Okay, so this is our Unit 1 test review. We've been talking about key features, graphing and solving absolute value functions, real-world absolute value functions, piecewise functions, all that good stuff. So number one, our questions 1 through 3, we're using these two functions on the right side, A and B. A, I notice, is a linear function. It's a straight line, right? And then for my function B, my x's go up by 1 and my y values aren't going up by the same number each time. So I'm not really sure what this is, but I'm going to sketch a graph so that I can answer these questions better. Always a good idea to sketch your graph so that it's easier to answer the questions. So I'm going to do -2, -8. -2, -8, -1, -1, 0, 0, 1, 1. So it looks like we kind of have a curve like this. So that would be an exponential function. All right. So for number 1, it says which function has the greatest x-intercept? So x-intercept is where the graph crosses the x-axis. And we want the greatest x-intercept. So looking at my graphs, it looks like function A crosses about, and looks like this is going by 2's 2, 4. Looks like it crosses about -4 for that x-intercept for function A. And then for function B, it crosses at 0. So if we want the greatest one, that would be function B, right? 0 is greater than -4. All right, number 2, which function has the greatest value at x equals -3? So when x is -3, which one has the greatest y values? What that is asking. So looking at -3, going to function A, so -3 would be right here. Looks like we're at about 1. And then -3 for function B is at -27. So for the greater value, or sorry, this is +1 over here. We're at +1. Oops, I don't know why it's racing. Sorry, my pen just glitched. All right, so at 1, or sorry, at -3, we're at a y value of 1 for A, and then we're at a y value of -27 for B, and we want the greater value. So that would be A, right? Because 1 is bigger than -27. All right, and then estimate the interval on which both function A and function B are negative. All right, so negative, that's when our graph is below the x-axis. So all of those negative y values. So looking at function A, looks like it crosses, the x-intercept is at -4. All right, that's where function A crosses. So function A is negative up until -4, right? And then we get positive y values. So for function A, it is negative from -infinity up until 4, right? We have all these negative x's up until that -4, sorry. And then for function B, we're trying to figure out where they both negative. So where do they overlap? So we're coming from -infinity for function B. -4 is way over here for function B. B is negative up until looks like 0. That's when it starts getting positive. So for the overlap, B is negative down here, up is negative up until -4, and then also negative after that. So for their overlap, it would be the -infinity to -4, because B is already negative at that point. All right, 4 and 5. So the graphs of m of x and p of x are shown. Describe how to move the graph of m of x so that it coincides with the graph of p of x. So for this one, m of x is being moved so that it's coinciding with p. So that means that m of x is the OG and p of x is the new. All right, and we want to know how are we moving m of x to get p of x. So if I look, m of x is centered at the origin 0, 0. And then it looks like they just took this whole function and moved it to the right, looks like 3 units. So the new vertex is at 3, 0. So it looks like we moved, or I'm going to say we did a horizontal shift, right? Because if we're moving to the right, we're horizontally shifting this graph to the right 3. So we moved it to the right 3 units. And then if we want to write the function p of x in terms of m of x, p of x is the new. So the p of x goes first, right? We're writing this p of x in terms of m of x. So we're taking m of x and we're taking m of x and we will be subtracting 3 inside the parentheses. Remember, with our horizontal shifts, we are inside the parentheses. And it's always the opposite of what you think it should be inside the parentheses. So we're going to the right 3, but inside the parentheses, we're going to be subtracting because it's that horizontal shift. Right, and we're affecting the x values by doing a horizontal shift. That's why we are inside the parentheses, right next to the x. All right, questions 6 through 9. Use the table of values for a of x, d of x, and h of x are shown. And they asked a few questions. So we want to first describe the shift from a of x to d of x. So they want to know what's happening, what's changing, and how is it changing. So if I notice, I'm looking from a and d, so my first 2 boxes. Right, for question 6. I notice that all of my x's are the same. They're all -1, 0, 1. So it looks like my y values change. -1, -4, 0, -3, 1, -2. Those are different. All right, and then I have to figure out how are they different. So it looks like if I did, let's see, looks like if I do 0 minus 3, that gets me -3. And then I want to check it, make sure this, whatever your like whatever you think is your transformation, make sure it applies to all of the y values. So -1 minus 3, that is -4, so that works. And then 1 minus 3, that is -2, so that one also works as well. Okay, so if we're subtracting 3 from all the y values, that means this is a vertical shift down 3. All right, so if we're affecting our y values and we're subtracting the same thing, we're going down 3 units. All right, so then if we wanted to write the function for d of x in terms of a of x, so d of x is our new. That always goes for the new function, always goes first. And then if this is a vertical shift, we're going to be on the outside of my parentheses, and we will be doing what we think it should be. So remember, horizontal shift is the opposite. With the vertical shifts, it is exactly what we think it should be. So we're going to be minusing the 3 on the outside of the parentheses. So we're taking a of x and just subtracting 3 from all those y values. All right, now they want us to do a of x first. So for number 8, they want us to do a of x and h of x. All right, so we want to describe the shift. So what's changing? How is it changing? So for this one, I noticed that all my y values are the same this time. So the x's are changing in this case. So I'm looking -1 to 4, 0 to 5, 1 to 6. It looks like we're adding 5 each time. Let's make sure it's right. So -1 plus 5 is 4. 0 plus 5, that is 5. 1 plus 5, that is 6. So it does work for all of the x values. So if we're adding 5 to all of the x's, that means that this is a horizontal shift right? Because we're affecting the x values. And if we're adding 5, that's going to move it to the right 5. Right. So if we wanted for number 9 to write the function for h of x in terms of a of x, so h of x is our new. Oh, oops, sorry guys. H of x is the new one, and we're equal to a of x. And in this case, we are inside the parentheses because it's a horizontal shift. And we're going to be subtracting the 5 because, again, with the horizontal shifts, it's the opposite of what you think it should be in the parentheses. So we're going to be subtracting 5 in the parentheses. All right, number 10 and 11. All right, so the table shows the table of values for m of x and n of x, where n of x is a transformation of m of x. Use the tables of values for questions 10 and 11. All right, so 10 says write a description of the transformation. So we want to see what's changing, how is it changing. So m of x to n of x. So m of x is the OG, n of x is the new one. So it looks like all my y values are the same, right? 3, 2, 1, 2, 3, 3, 2, 1, 2. This should be a 3 right here. I think that's a typo. So all of the x's are changing. Yes. So how are they changing? Let's look. So -2 to 5, -1 to 6, 0, 7, 1 to 8, 2 to 9. Looks like I'm adding 7 each time. So 1 plus 7 is 8. 2 plus 7 is 9. 0 plus 7 is 7. Yeah. So it works for everything. -1 plus 7 is 6. -2 plus 7 is 5. So we're adding 7 to all the x values. So that's going to give me a horizontal shift. And if we're adding 7, we're going to the right 7. And then for the type of transformation, this is where we want to write an equation for this. So we want to take n of x, or sorry, we want to take n of x and write it in terms of m of x. Now, if we're going to the right 7, it's going to subtract 7 inside our parentheses because we're doing the opposite. And so our k value would be -7. Right? You might think it's +7, but remember, for the horizontal shifts, it's always the opposite of what you think it is. All right, cool. So next one. This is an absolute value graph, and we're going to use this graph to sketch the graph of, they give us the parent function, absolute value of x. They want us to sketch the new graph. So thinking about this, if I'm subtracting a 5 inside my parentheses, or sorry, absolute value bars in this case, that means we're going to the right 5. And then if I'm subtracting 2 on the outside of the absolute value bars, that means we're going down 2. And we also learned that in this equation, in this form of the absolute value equation, this is in the x plus h plus k form. Sorry, I think it's minus h in here. H and k are our new vertex. So h in this case would be +5 and k would be -2. So our new vertex is at +5, -2. And we can see that by going right 5 and down 2. And then there's nothing in front of my absolute value bar. So there's no stretch or compression factor to this graph. And so we can use that to help us graph the rest of the lines. The lines are not going to get any narrow or wider, so the slope of each piece will remain 1. We talked about this in class, how like if there's a number in front, it makes your slope either more narrow or wider, but nothing happened to the slope, so we can go up 1 over 1 and get a few more points in order to draw the rest of our graph, rest of our new graph. That is a horrible line. Let me redo that. Let me get thicker line for this. All right, so now that we have our new graph, we're going to answer our key feature questions. So the x-intercepts, looks like I have two x-intercepts in this case. So it looks like I cross at -3 and +7. So I cross at -3, 0. Or sorry, not -3. I don't know what I'm saying. +3, that is +3. And +7, 0. Sorry about that. Just got to keep you guys on your toes. So this is +3 and this is +7. Sorry, our two x-intercepts. The y-intercept looks like it's up at +3, so 0, 3. Our vertex we said was 5, -2. I'm going to do domain first. Domain for all of our absolute value functions, we know that is all real numbers. Range. So we want to scan from bottom to top. So it looks like I start getting y values at my vertex, and that y value of that vertex is -2. So we start at -2. And we put a bracket around -2 because we include -2 in our interval, right? We have a point at -2 on our graph. Right, and then I have everything above -2, so my range values go off to +infinity. There's no place when I'm looking up from this graph that it would stop. So our y values go to +infinity. And if we wanted to write this in inequality notation, you would say that's y is greater than or equal to -2, because we are equal to -2 and then we want everything above. And then this graph opens upwards. All right. Increasing and decreasing. All right. So increasing and decreasing. I told you guys, imagine a little person walking on your graph. He's going down, 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 down. So he is decreasing. And remember, we always want to use the x values. So for what x values is our little person going down the graph? So it looks like I have all these negative x's over here. So from -infinity up until he gets to the vertex, so up until 5, that's when he'll start going up. So he's decreasing from -infinity up until 5. And we put a parentheses around 5 because he's not increasing or decreasing at 5. Right? We've talked about this idea of at the vertex, he's just chilling, right? He's just standing at the vertex. He's not going up, he's not going down, he's just sitting there. Right? But this is where he starts going up. So we start at 5. And again, we're putting a parentheses around it because we're not including it in our interval. And then he keeps going up forever and ever to +infinity. Oh, that was horrible. +infinity. Okay. And again, parentheses around infinity signs always because we can't be equal to infinity. All right. Word problems. Let's go. All right. So Danielle rode her bike to the park and then home again. The graph models her distance from home in terms of time in minutes. All right. So just some observations first. Danielle's riding her bike. She's going to the park and then she's going back home. All right. The graph looks like on the x-axis, I have time and they're measuring her time in minutes. So we're inputting time into this function. And then for some amount of time, she's going some amount of distance, which is our y values. In this case, they're measuring it in miles. So we're going to answer some questions. So 13 says, during what interval was Danielle's distance from home decreasing? So where is she going down? So let's think about, okay, Danielle is on her bike. I don't know how to draw a bike, so I'm just going to draw her walking. So where does she start going down? So it looks like when she gets to like the peak up here, the vertex, that's where she starts going down. All right, so we're going to use that x value of the vertex. So it looks like she starts going down at, looks like this is going up by 10. So 10, 20, 30, 40. So she starts going down at 40. All right. And then at the vertex, again, she's not increasing or decreasing, right? She's just chilling at the top of that vertex. So we're going to put a parentheses around 40. So we don't want to include it in the interval. Sorry, I can't write. Okay, 40 parentheses. Now she's going down, 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 down. Now, this function is graphed for every x and y. But if we want to think about this in the context of our problem, looking at this part where the graph crosses the x-axis, it doesn't make sense for us to be negative because, so it doesn't make sense to have this part of the graph because y is distance, and it doesn't really make sense to have negative distance. All right, so we're gonna say like this part of the graph is restricted. We're not actually gonna get any y values down here. So she's deep. So because normally we would say, okay, it goes off to positive infinity, right? X gets bigger and bigger, the graph keeps going on forever and ever. But once she gets to this dot right here, she's stopping because she's not going negative distance. Okay. So this looks like it's 60, 70, 80. So up until 80, that's where she's decreasing. And if we want to think about this in the context of the problem, if this is representing distance per time, this means that at 0, that's where she starts, right? That's when she leaves, okay? She's leaving 0 time, right? No time has passed. She's riding her bike. She's going some amount of distance. And then at 40 minutes, her distance starts decreasing. So this means that like for like this part of the graph over here, that's like her going to the park, and then she's at her like peak distance away from home, and then she's going back home is like the second half of the graph, because once she gets like a distance of 0 again, then she's back home. So with our word problems, it's helpful to like think, okay, what am I looking at? What does this mean? How can I interpret this of what my problem is asking me to interpret it? All right. And then for the last part of this, she's not increasing or decreasing at 80, right? She's back home. She's not going anywhere. So we're not going to include that. Oops. We're not going to include that in our interval. So we're going to put parentheses around it. All right. Next question. What key feature? I'm going to erase all this just to answer these other questions. What key feature shows Danielle's maximum distance from her home? So I kind of just mentioned this. So this half of the graph over here is her like going to the park, and then she gets to some max distance away, and then she starts going home on the right side. So the vertex, that would tell us like her maximum distance from home, because it's saying like, all right, this is the peak of the graph. We can't go any further than that, right? And if we want to also think about it this way, is like up here, I'm not getting any more y values above that vertex. So this vertex at this y value, which looks like 3, so 3 miles in this case, like that's the furthest she goes from home. We're not getting any more y values above that. So the vertex represents that maximum distance. All right, and then what key feature, number 15, what key feature shows the time it took Danielle to return home? So thinking about this, she starts at 0, right? 0 time, 0 distance, she hasn't gone anywhere, right? And then once she gets over here to 80, so x equals 80, that's when she's back at home, right? First half of the graph is when she's on the way to the park. Second half of the graph is when she's coming home. So it's asking us what key feature shows that time it took for her to come home. I would say it's those x-intercepts, or you can say it's like the domain, because the domain is ranging from 0 to 80, and the domain tells us the time. Right, so our domain starts at 0 time, ends at 80 minutes. So she's been gone for 80 minutes. So that tells us the time it takes her to leave and come back. Right, so either one would work for that, the x-intercepts or the domain. right? And then 16 kind of goes along with this question. What is a reasonable restriction on the domain? So we want to start at 0, right? That's where she starts, 0 time. And then up until 80, right? She's gone from 0 to 80 minutes. It doesn't make sense for us to have any negative time, so anything before 0. And it doesn't make sense for us to have anything after 80 because we can't have those negative y values as we talked about a few minutes ago. And we're putting brackets around both of these because we do have dots at both of those, right? She can be equal to 0 time, right? She hasn't moved yet. Danielle hasn't started riding her bike. And then we can also be equal to 80 minutes because that's like the exact time when she gets back home, right? And then if we wanted to write this in inequality, this is interval notation. If we wanted to write this in inequality notation, we would have x greater than or equal to 0, but also less than or equal to 80. So x is between that 0 and that 80. Okay, and then our last question, 17, the point 20, 1.5 on the graph, and then they want us to interpret that. So going to 20 up to 1.5. 20 is the x, 1.5 is the y value. And in this case, x is time and y is distance. So for this problem, this means that after 20 minutes, so because the x is minutes, and then she's going some amount of distance, so she went 1.5. Sorry, she went 1.5 miles. So after 20 minutes, she goes 1.5 miles. All right. All right, 18, solve the equation by graphing. All right, so for this one, we're going to graph and then solve, and then we're going to verify the solutions algebraically. So to graph this, I'm going to plug in some x values and get some y values. So I'm going to just make like a t table. I'm going to plug in some sorry, give me one second. Okay, so this is equal to 6. So we know that we're going to have this horizontal line at 6, right? Because they give us this like y equals 6 line. And then if we wanted to think about this function as negative 3x minus 9 equals y instead, I'm going to plug in some x's and some y's to see what would I get for y. So I'm going to plug in, let's do negative 2 first. So if I plugged in, if I plugged in negative 2, that would give me negative 3 times negative 2 is 6 minus 9 equals y. So that'd be the absolute value of negative 3 equals y. So negative 2, 3. We'll plot that on my graph. I'm plugging negative 1. So I plug in negative 1, that would give me 3 minus 9. So absolute value of negative 6. So 6. Okay, looks like my graph is going up. So I'm going to plug in something less than negative 2, so negative 3. So if I plugged in negative 3, that would give me 9 minus 9, which is 0. Okay, so that's going to be my vertex. And since this is an absolute value graph, it's symmetrical, so I can just kind of mirror everything over the absolute value, over the vertex. So I'm going to have another point at negative 4, 2. And then also another point at negative 5, 5. right, so it looks like solving this, it would be x is equal to -5 and x is equal to -1. Right, that's where these two lines are crossing with the x values, right? So now we also want to verify it algebraically. So we need to set up our two equations. So we want to do the positive case, so -3x minus 9 equals 6. And we also want to take into account the negative case, so equals -6. So doing this, I would add 9 to both sides for the first one on the left. So -3x equals 6 plus 9 is 15. And then I want to divide both sides by -3. So x equals -5, which we did get. So that's one of them. Bad check mark. Ooh, check mark. And then we're going to add 9 to both sides on this one. So -6 plus 9 is -3. Divide both sides by -6 plus 9 is +3. Divide both sides by -3, you get -1. So good. So yeah, so both of our answers check out. All right, 19 through 23, we are solving these absolute value equations. So again, we want to do positive and the negative cases. But first, like for 19, we have to get rid of this 4 first. So we're going to add 4 both sides. And we'll have 4x plus 10 equals 12. And then we also want to get rid of this 4 in the front of the absolute value. So we divide both sides by 4. So x plus 10 equals 3. All right, so we got to do both cases. So both the positive case and the negative case. So we have the x plus 10 plus equals 3. And then we also need to take into account that this could be equal to x plus 10 equals -3. So for this first one, it would be x equals, subtract 10 on both sides, it would be -7. Subtract 10 on both sides for this next one would be -13. Which will get -7 and -13. All right, next one. All right, so if you're equal to 0, we know that there's only going to be one solution, right? We can't do a positive and negative case for this. Right, there's no such thing as +0 and -0, it's just 0. So we're going to just add the 8 and get 5x equals 8, and then divide both sides by 5. So x equals, just leave it as a fraction, 8/5. All right, number 21. Again, we got to get rid of everything about around my absolute value before I do my positive and my negatives. So I'm going to get rid of this -2 first. So I'm going to add 2. I'm going to have 2 absolute value bar x plus 5 equals 2. Then we also got to divide both sides by 2. So x plus 5 equals 1. And we also need to do x plus 5 equals -1. So I divided both sides by 2 to get rid of this 2 in the front. That's how I got the 1. And then I'm doing the negative case now. So then to solve, we would just subtract 5 on both sides. So x equals -4. Subtract 5 on both sides for the other one. So x equals -6. All right, number 22. I noticed that the equation is equal to a negative number, and there is no way that an absolute value can be equal to a negative number. So we know this one is no solution. All right, 23. Got to get rid of this +7 first. So got to get rid of everything around our absolute value bars before we start doing the positive and the negative case. So we're going to subtract 7 on both sides to get rid of the +7. I'm going to have absolute value bar 5x minus 28 equals 13. I'm going to rewrite this over here so I have more room. Whoops. So 5x minus 28 equals 13. And then we also want to do 5x minus 28 equals -13. All right, so plus 28 first on both sides. So 5x equals 41. And then divide both sides by 5. So x equals 41 over 5. Just leave it in the fraction. All right, next one, add 28 on both sides. So 5x equals negative 13 plus 28 is 15. Divide both sides by 5. So x equals 3. 2 solutions for that one. All right, last problem, piecewise function. All right, so piecewise functions, those are made of pieces, right? Looks like we have 3 different pieces for this one. Looks like I have a quadratic piece. So I got an x squared in there. I got a 2 raised to the x power. So that would be an exponential piece. Right? We have a variable in our exponent. And then looks like I have just a linear piece on the end. So we have 3 pieces, quadratic. So we know this is going to kind of look like a parabola. Exponential, so it'll look like a curve. And then we'll have a linear, we'll have a line. Right, so it's a good idea to just like give yourself a visual, like what is this going to look like when I graph it, or what should it look like when I graph it? They first we want to do the table of values, right? That'll help us graph this. So we're going to just plug these numbers in. So let's starting with the quadratic piece on the left. So plugging in -4, I'm going to have -4 squared plus 4 times -4 plus 5. So 16 minus 8 plus 5. That's going to give me 5. Wait, no, that's wrong. Sorry. 4 times -4 is 16. My bad. Okay. So 16 minus 16 plus 5, that will give me 5. 5 is right. I just did it wrong up top. Sorry. All right, plugging in -3, I'm going to have -3 squared plus 4 times -3 plus 5. -3 squared is 9 minus 12 plus 5. That would give me 2. All right, I'm going to erase this. All right, plugging in -2, that's going to give me -2 squared plus 4 times -2 plus 5. So that would be 4 minus 8 plus 5, so +1. And then plug in -1, so -1 squared plus 4 times -1 plus 5. So the 1 minus 4 plus 5, which would be +2. All right, so it's kind of tedious, but we're just plugging in some numbers. All right, now we're going to do the exponential. So 2 to the x. So 2 to the -1. Sorry, my pen keeps freaking out. All right, 2 to the -1. And anything with the negative exponent becomes a fraction, and the exponent becomes positive. So 1/2 or 0.5. Right, 2 to the 0. Anything to the 0 power is 1. 2 to the first power, that's going to be 2. And then 2 squared is 4. This one, I don't know what's happening. 0.5, 1, 2. Sorry. All right. Last one, the linear one, plug it in. So -1/2 x plus 4. We're going to plug in 2. So I'll have -1/2 times 2 plus 4. -1/2 times 2 will give me a -1 plus 4. So 3. All right, plugging in 4, I'm going to have -1/2 times 4 plus 4. -1/2 times 4 is -2. -2 plus 4 is 2. Gonna erase this. All right, 5 will have negative 1/2 times 5 plus 4. So that'd be negative 5/2 plus 4. Common denominator, we can change this 4 to a 4/1. Multiply it by 2/2, so I get negative 5/2 plus 8/2, which would be 3/2. So 1.5. And then lastly, plug in 6, we'll have negative 1/2 times 6 plus 4 will give me negative 3 plus 4, so positive 1. Great, so we're gonna graph now. So we're gonna graph our pieces. I'm starting with my quadratic piece over here. So I'm at negative 4, 5. I'm gonna thicker. I'm at negative 4, 5. I'm at negative 3, 2. Negative 2, 1. And negative 1, 2. Now, this is where we need to check our domain. So in my piecewise, for the quadratic, x is less than negative 1. So that means at this negative 1 point, I'm going to have an open circle. So negative 1, 2, I'm going to have an open circle because we can't actually be equal to negative 1 for this quadratic piece. So that gives us that open circle. And then connecting the dots kind of looks like a little more than half of a parabola, which is correct because this is a quadratic. All right, now we're going to do the next one, the exponential. So for this one, I want to look at my domain to make sure I'm doing everything correct. So the negative 1 I can actually be equal to in this case. So for the negative 1.5, I actually can have a closed dot right there for this piece of my graph. And then 0, 1, 1, 2, and 2, 4. And again, I need to check to make sure. So I actually can be equal to 2, so I can have a closed dot there. And this is starting to look a little bit like a curved exponential function. All right, and then lastly, our linear piece starts at 2. And we're only greater than, so we're going to start with an open circle for this one. So for 2, 3, I need an open circle at 2, 3. And then 4, 2, 5, 1.5, 6, 1. Yeah. That's my linear piece. All right, now we're gonna answer all these questions that they got done here. So increasing and decreasing. So where is my graph going up? So it looks like if I think about a little person on my graph, looks like from like over here, we're going down. So we're decreasing. That parabola goes on forever and ever to the left. So from negative infinity, we're decreasing up until the vertex of my parabola. Then I start going up. Whoa, I don't know what just happened. There we go. Then I start going up. So up until that vertex, which the x value is negative 2, I'm decreasing. Then it looks like I'm going up that rest of the parabola, and my exponential function's also going up right there. And then we want to make sure there's no other parts of this graph going down. If I look to the right side, looks like over here at the linear piece, I do start going down again. So that linear piece starts at positive 2. So we have this interval, negative infinity to negative 2. Or we have another interval starting at positive 2. And then looks like that linear piece goes down and down forever and ever. So positive infinity. The x's are going to positive infinity. And we have parentheses at both of these, like -2 and 2, because if we look at our graph, whoops, I keep doing that, I'm sorry. At the vertex, right, we're not increasing or decreasing. We're stationary, we're not going anywhere. And then at this +2, I'm not actually equal to +2 right there for the decreasing interval. Like my person, that part of the linear piece has an open circle, so we don't include that either. So that's why we have parentheses around the -2 and the +2. And we always have parentheses around our infinity signs. All right, increasing. So looks like at the vertex of the parabola, that's where we said he started, our little person started going up. So at this vertex, right, that's where we start going up. And my exponential part of the graph is also going up over there. So at the vertex, so at -2, and again, at the vertex, we're not going up or down, so we don't include it, so we put a parentheses. He's going up. And we do have a point on the exponential right here at -1, so we're good there. We have an open circle, but we also have a point, so we kind of have covered that. And then he's going up, up, up until 2. That's where we said we were starting to go down. So from -2 to +2, our graph is increasing. All right, positive and negative. Positive intervals are where my graph is above the x-axis. So where am I getting positive y values? So looking at this graph, I'm going to erase my little person. And try not to erase my graph while I'm doing it. Here we go. Looks like we are positive up until over here. Right, my graph, like this quadratic and this exponential and this first part of this linear, is all above the x-axis. So all these negative x's, so negative infinity, up until this dot right here, that's where I stop being positive. And it looks like 8, but let's just make sure. This is the linear piece, so I don't know what just happened, guys. Let me. There we go. I don't know how to get back. Oh, here we go. Here we go. Sorry, technical difficulties. All right. So what was I saying? Oh yeah, we're trying to figure out what this point is right here. So I'm gonna plug 8 into the linear piece. So -1/2 times 8 plus 4 will give me -4 plus 4, which is 0. Good. So up until 8, we are positive. And we don't include 8, right? We put a parentheses around 8 because 0 is neither positive nor negative. So parentheses. All right. And then negative intervals, that we start getting negative after the 8. So we start at 8, don't include it, and then that linear piece goes on forever and ever as x gets bigger and bigger. So x goes to positive infinity. So we're negative below, or sorry, we're below the x-axis, everything after 8. And again, we don't include 8, we put a parentheses around it because at 8 we're 0, and 0 is neither positive or negative. All right. And the questions on the right, identify the y-intercept. So we want to just see, where does this graph cross the y-axis? That's on our exponential piece right there at, we can see that at 0, 1. So 0, 1. And then how many solutions are there to f of x equals 1? So when the graph is equal to 1, so right here on the y, right, that's 1 right there. We have a point on the parabola, we have a point on the exponential graph, and we have a point right here on the linear piece. So I have 3, and you can also see it in our table of values. We can see that there's that y value of 1 occurs 3 times. So there are 3 solutions. And then lastly, we want to know the solution to f of x equals 5. So where is the y value? 5. Or sorry, what's the x value when y is 5? So looking at 5, looks like it's on the parabola. And I'm going to look at my table of values for the parabola. Looks like it's at x equals -4. That's where y is equal to 5. All right, that is it for your Unit 1 review.